recording? You used to
Yeah.
do Thanks. I should say, and you'll learn why using a microphone like this is really hard when I do this. So thank you very much for turning up. I'm going to start quickly rather than our usual way because it's going to be a jam-packed afternoon of science and fun. So welcome to this celebration, the 2023-24 Southampton SAO Astronomy Masters Programme that's been run by Professor Diego Altamirano. I always get Diego's name wrong. Over in the UK, and hopefully Diego is able to be watching us now on the mighty Zoom. So each year, for most of the years of time I've actually been in the FAO, this programme has taken 5 of the top master's students who were just discussing whether they were technically the top, almost the top, and it's very complicated, from Southampton. And they spend a year, or really 9 months, on a research programme. They've already presented works, their preliminary results over the AAS over in New Orleans. And they're now going to tell us about what they've been doing. And then they'll also be presenting a final Viva in Southampton in, what, 2 weeks?
1 week.
In a week, sort of thing, along with their programme, the project report that they've been part of. So there's a lot of work that they've done. And so before we start the presentation, I'd just like to make 3 notes. One, as I mentioned, please send in your project report ideas, your project ideas for next year's students who will be coming up in. When did you start? Is the end of September or start of September? Start. So please send them in as soon as possible. It's a great way to get bang for your money, and like you've given our current budgetary constraint. You don't listen to the facts of the current people who do this. I'd like to thank the Head Lunch Talk organisers for letting us have this proposal, for having this time. And finally, I'd like to thank our admin staff. Not be able to do this without them, and so in particular, Catherine Murphy's work in helping me transition, taking over from Jeremy Drake doing this. So turning to today's programme, we'll be spending our time switching between sorts of high redshift, quasars of redshift 1 or 2, and low redshift stellar systems in the galaxy. So for anyone currently writing a programme, can we have something in between those two? Sorry. So first, we're going to start with Maja Cummings, who's been working with Mohigan Azadi, who wanted us to know, and sorry about this, this is somebody from Mohigan. She wanted us to know that Maja had been very ambitious, self-motivated, hard-working, and I guess impressed all of us in the things see our collaboration. And it's a nice spoil the end of Maja's talk, but Mohigan wanted us to know that Maja has finished the draft of the paper on her research that will soon be submitted to the adjunct. So, Maja, will you tell us about the relationship between quasars and their host galaxies' properties at cosmic rays?
Okay. Hello, everyone. Can everyone hear me right? Is the volume good? Yes? Okay. So, as I have been introduced, I am Maja. I have been doing my master's project here under the supervision of Maja Cummings, and I'm here to talk to you about that project, and it is on the relationships between quasars and their host galaxies' properties at cosmic noon. So why are we interested in this topic? Well, first of all, we know that there is a supermassive black hole at the center of virtually every massive galaxy. And we know that sometimes these supermassive black holes start rapidly accreting matter and they become AGM. But we don't actually know what causes this switch to happen. It's quite a big mystery in the field. And understanding how AGN affect their host galaxies can help us understand more about the processes that ignite them. And we are also interested in this relationship from a galaxy evolution standpoint. We suspect that AGM most likely play a big role in shaping galaxies. And so understanding what this role is helps us understand how our present-day galaxy population came to be. So there are a number of results that make us think that AGN and their host galaxies are interacting. And these are the 2 most important ones. So here, On the left-hand side, we have a graph with supermassive black hole mass against galaxy bulge velocity dispersion. And it's quite a noisy graph, but the most important thing is that there's a significant correlation, positive correlation between these two. And here on the right-hand side, we have a scaled accretion density on the y-axis, or star formation density. And on the x-axis, we have redshift, or look-back time. And here we can see that the best fit star formation history of the universe and the massive black hole accretion history are evolving together simultaneously and peaking at about a redshift of 2. And we call this epoch cosmic noon. And then they decline in tandem together. So all of these are implications that AGN and their host galaxies are connected. But how do we look at this connection? Well, there are a number of ways. So we narrow it down to this specific question we look at. Is there a statistical correlation between AGN luminosity and star formation in the host galaxy? And well, we are not the first people asking this question. There has been extensive research on this topic, and the results are diverse. So some studies find negative correlations, some studies find positive correlations, and some find no correlation at all. So initially, one might think that what's going on? Do most of these studies just get it wrong? But as research progresses, it becomes obvious that perhaps the answer to this question is simply different depending on the sample that we look at, the redshift range we probe, and things like our choice of tracer for star formation and AGN activity. So we narrow it down. Let's take a look at what is happening in radio-allowed quasars above a redshift of 1. This is a particularly interesting population to look at because radio-allowed quasars are thought to be depositing an immense amount of energy into their surrounding medium. And also the redshift range between 1 and 2 is the epoch of cosmic noon that I mentioned previously. So a sample like this is what we would think would show the strongest interaction between AGN and host galaxy. So for this purpose, we have picked 20 quasars from the second revision of the third Cambridge catalogue. These are the number of quasars that satisfy these criteria within this catalogue. They are type 1, they are radio-loud, and they correspond to the epoch of cosmic noon. So the next step is to investigate the properties of these systems. And for this purpose, we turn to SED modeling. Namely, we use the AGN radio to X-ray modeling code ArcSed. And as its name suggests, it models the SED all the way from radio to X-ray, covering 10 decades of frequency. And it works by fitting all of the different components in the AGN host galaxy system and then coming up for a fit for the entire SED. So here is the result of this fitting process for one source, 3C9. And as you can see, we have radio emission from the radio structures. We have infrared emission from the torus. We have emission from the host galaxy all the way between the sub-millimeter and the UV. And then we have the brightest region. We have emission from the visible to the X-ray from the accretion disk. And from this process, we get two very important properties. One is AGN luminosity, bolometric AGN luminosity, and we get it by integrating the accretion disk all the way from near infrared to X-ray. And this is what we will be using as our AGN activity tracer. And we get star formation rate by fitting the galaxy emission with the fitting code MagFizz. This estimates star formation, mainly relying on this far infrared bump right here. And that brings me to the big result. Is there a connection between star formation rate, bolometric luminosity? And it looks like there is. You can see Spearman's correlation coefficients here in the upper left-hand corner. Generally, a p-value of smaller than 0.05 is considered significant, and we have 0.03. So it seems like there is a significant correlation between star formation rate and AGN luminosity, and it is a positive one. So brighter AGN tend to reside in galaxies with higher star formation rates. But we take a look at another piece of this puzzle, and that is jet length. Jet length can be, this is the length of the radio jets, and it can be considered a proxy for the age of the source. So we measure them using archival radio images. We measure them lobe to lobe. We estimate their length using Ned Wright's cosmology calculator and deproject them using inclination angles from a paper by Marin and Antonucci, this 2016 paper. So we get the true deprojected jet length size. And when we plot star formation rate against this length, we actually end up seeing no correlation. So what does this mean? Well, it contrasts with other papers that have found that younger jets are better at triggering star formation. This would be true in the picture where short jets are interacting with the ISM because they are within the confines of the host galaxy. And as they evolve out of it, this star formation triggering stops and the stars evolve passively. So why do we not see this? Where there's a chance that maybe all of our jets are too large. They have all evolved past the confines of the host galaxy. This might not be true because, as you can see, we have quite a few sources here under, like we have 5 sources under 100 kiloparsecs, and they have quite a range of star formation rates. So there seems to be no connection here. Another possibility is that the picture is just more complex than what you can see with the statistical correlation. There might be complex interactions involving triggering and quenching. There also might be disparities in the timescales of jet growth and star formation. And of course, the very last possibility is that there is simply no jet-induced star formation at all. And we take a look at a last piece of the puzzle we will be looking at, and that is major mergers, because there are many theories that a correlation between AGN luminosity and star formation rate arises due to them sharing a source of fuel. And this source of fuel can be accreted from the cosmic web, but it can also be introduced through interactions with other galaxies, most prominently major mergers. So these can not only introduce new fuel, but they can also disrupt gas distribution, and they can funnel gas into the central black hole, fueling both star formation and AGN activity. So to investigate whether this is present in our sample, we use the work of Briding et al., who visually inspect high-resolution HSD data and use 6 experts to identify subtle merger features and categorize them into different merger categories. And we end up seeing that 17 out of our 20 sources show signatures of 1 or more merger categories. So this is the majority of our samples, and they show this distribution and categorization right here. So this supports that there might be a connection between, or the mergers might be behind the connection between the AGN and star formation rate. Overall, our conclusion is we do see some connection between AGN activity and star formation rate. This could be due to some process that is due to AGN accretion actively fueling or actively triggering star formation. It could also just be due to some shared fueling mechanism. We also don't see a correlation between jet length and star formation rate, but this does not necessarily mean that the jets are not playing a part in triggering star formation here. It might just mean that the picture is more complex. There's complex interactions going on in the galaxy, and variations in timescale also may complicate things. So overall, all of these aspects play into the result we see, and that just highlights that there is more research to be done in this field. Thank you very much for your time.
Okay, questions?
I have a question about your sample, which is very small, with 20 sources.
Yes.
So you have conclusions which are more general. I was wondering how
Yes, okay.
you can make those conclusions based on small sample.
So yeah, that was most likely an issue with my communication. Our conclusions are specifically for this sample. And yeah, a big part of this research is that the results are very sample dependent. So these conclusions are possibly for most high redshift radio loud type 1 quasars, but all that we know for certain is that this is what is happening in our sample. But yes, you're very right. We can't, this is not a global conclusion. But yes.
Thank you, Maja, very nice presentation. So in your main result where you find a positive correlation,
Yes.
I was wondering what is the magnitude of your Barton point? And if it goes, if you have the, where does it find you are?
Yes.
Wait.
So, there is an issue with calculating uncertainty in our research, separately for star formation rate and AGN luminosity. For star formation rate, MagFizz actually returns uncertainties, but the uncertainties it returned were very unreliable. It would return big uncertainties for a couple sources, which is what we'd expect on some values, but then it would return 0 for other ones. So we couldn't actually figure out what the issue was so far. So we decided not to include these uncertainties because it's probably wrong. And AGN luminosity, we didn't calculate uncertainties because it would require quite a lot of computational power, because we calculate the AGN luminosity from the best phase accretion disk, and that has a lot of variables, and each of them have individual uncertainties. So yes, that is a limitation of our study, that we haven't really paid attention to this, but this is something that I will plan to investigate as I plan to publish the paper. We will calculate all of these.
So Yazmin, can you use this?
This
Change presentation. I might need to stop sharing.
Yes, you should stop sharing.
Boy.
Oh no.
My Zoom is closed. There's no Zoom open.
It seems to be open. Can you search?
Who's been working with Mercedes, so the Morales on
Well, that's very strange.
Now, Mercedes says that she is impressed by how Maria Lilley has grown into a real life scientist in such a small period. And not to be outdone by Maja, Maria Lilley is planning to collaborate with Mercedes on more data on a target.
I think it's just in a different window.
I
don't know how to use it.
It's okay.
Oh, no, don't
do that.
So you want?
Yeah, it's just open in a different window.
Discussion goes. And we tell us about the atmosphere of the 900K sub-Neptune, which
Yeah. Okay, so you're now sharing your.
So if I do,
what's
Wait.
lines of the.
yeah,
I forget how I learned
Let's
to love HST schedulers.
if I just put this in PowerPoint presentation video, can I do it? I'm still seeing on the TV. Wait, this says like, see this, can you see this? So like, it's heaven, isn't it?
I can't.
Oh, yeah.
I think we might have to go over here. Let's close.
It's the owl stops.
No, actually, I think it's when we accidentally close.
Is it when we close the menu?
Yeah. What's this? Eggs and show.
Oh, okay.
Okay.
Yes.
All right.
There we go. We're back.
Okay. The external display got disconnected when I did that.
That's one of those ones. Okay, you're still.
No, it was line. Okay.
Yeah.
Let's try which is
That
it's
next
this
one.
talk.
Yes.
Okay,
And
well,
I need to reshare screen.
and it's not on Zoom, so we just need to go here. Share screen. And this one.
Yep.
Now let me close this. And you can just
Yeah. Where's my mouse? No, where's my mouse? Just there. I'll take a shot.
Right. I think that's okay.
Okay.
I think so. If everything's worked out.
It's good.
So hi, I'm Maria Lenny, and today I'll be talking to you about my master's project, which was on the characterization of the atmosphere of an 800 Kelvin sub-Neptune with transmission spectra from the Hubble Space Telescope. So to begin with, I wanted to say a few words about sub-Neptunes. So as I'm sure you're all aware, the Kepler mission was very important for exoplanetary science. And one of the most important findings was that sub-Neptunes, which are planets between the size of Earth and Neptune, are some of the most abundant type of planets in our galaxy. And another very important finding came in 2017 when Fulton et al. Discovered that there's a dip in exoplanets in sub-Neptune distributions. And this dip is called the radius gap. It occurs at approximately 1.8 Earth radii and effectively splits the sub-Neptune distribution into two distinct populations. Planets left of the radius gap, shown here in red, are called super-Earths, and they're more like terrestrial planets in our solar system, so they're more rocky and gas-poor. And planets right of the radius gap are called sub-Neptunes, they're more like the ice giants in our solar system, so they're icy and gas-rich. We're not entirely sure what caused this discrepancy between the two populations. However, there's two main theories. The first one is that they formed as independent populations, and then the second one is that sub-Neptunes evolved into super-Earths through mass loss. Why do we care about sub-Neptunes? Well, there is no solar system analog to sub-Neptunes, so we actually know very little about their formation, history, and evolution. However, we can learn a lot about them through population studies, as by studying their atmospheres, we can relate different scenarios about their evolution, formation, and history. And that brings me to a short introduction on sub-Neptune atmospheres. So sub-Neptunes can consist of condensates, which block light and cause featureless transmission spectra. And these condensates can include clouds, which act as a sort of gray filter, blocking all radiation. And they're caused by condensation of vapor, much like clouds on Earth. And that can also include hazes, which are caused by photochemistry. However, if condensates are not present in the atmosphere and the atmosphere is clear, we can detect spectral features of different species, including hydrogen, water, helium, methane, and carbon monoxide. And here I show the current theory, which is that depending on the temperature of the planet, different atmospheric conditions can be observed. So between 300 and 500 Kelvin, we expect a clear atmosphere. Between 500 and 800 Kelvin, we expect to see an atmosphere dominated by condensates. 800 and 1000 Kelvin is the expected transition between methane to carbon monoxide in the atmosphere. And then from 1000 to 1400, we expect to see a clear atmosphere again. And all of this graph shows the 8 targets of the space program, which I will introduce in a minute. But our target is shown in a red circle, and it is a sub-Neptune of 800 Kelvin. It's called TI-561c. It has a radius of 2.91 Earth radii and a mass of 5.39 Earth masses. I showed here compared to Earth just to see kind of the size difference. As I mentioned before, it's part of the space program, which studies the atmospheres of 8 sub-Neptunes of different masses, radii, and temperatures to just kind of see where the transitions between atmospheric conditions might occur. And we studied TI-561c with Hubble Space Telescope Wide-Field Camera 3 data, specifically in the near-infrared range, covering 1.1 to 1.7 microns. Why do we choose this range? It's because it allowed us to test 4 main atmospheric models for TI-561c, which were a clear atmosphere, one dominated by weak clouds, medium clouds, and a completely opaque atmosphere. And we studied TI-561c across 3 visits from November 2023 to February 2024, and each visit had 5 orbits of the HST. The observations were conducted with the G141 GRISM, which is shown here for reference. It took 110 spectral images, an example of which is shown here, and that's per visit. And then the F139 filter took 1 direct image per visit, and a very zoomed in image is shown here. And the direct image is shown just for position determination. And then the Wide-Field Camera 3, we employed the Wide-Field Camera 3 scanning mode, in which the telescope nods vertically during exposure. And each visit lasted 6.56 hours total, with a 3.75-hour transit each. We reduced the data with Pacman, which is a pipeline specifically developed to analyze Wide-Field Camera 3 data. It requires as input at least 1 direct image, multiple spectral images, and planetary and system parameters, and is split into 30 stages, which I'll describe here. So stage 0 sorts the observations into visits and orbits, depending on the exposure time. Stage 1 tracks the location of the Hubble Space Telescope in order to perform the barycentric correction, which is done in stage 2. Stage 3 plots a plethora of stellar models, which are then multiplied by the GRISM's throughput to create a reference stellar spectrum that's used for wavelength calibration. Stage 10 finds the center of the direct image and uses that to match the center of the spectral images. Stage 20 finds the trace of the spectrum, and that prompts the pipeline to perform an optimal extraction algorithm to extract the one-dimensional spectrum, which is then binned in wavelength bins in stage 21, and then the flux between each of those bins is integrated to extract the spectroscopic light curves. And here show the white light curves were extracted for all 3 visits. I also plot the ingress, egress, and mid-time of the transits just to show kind of what data were in transit, what data were out of transit. And on the left-hand side, I show the flux and the time in barycentric Julian date, and on the right-hand side, the normalized flux versus phase. And the flux was normalized by dividing each point by the average out-of-transit flux, and then the phase just refers to orbital phase. And it's important to note that visits 2 and 3 have been shifted back by 4 and 10 periods respectively, and that was just done so that we can plot all the visits in the same graph. Using this data, we can calculate the transit depth to be 0.03, which is a lot bigger than expected transit depth of 0.001, which prompted us to remove visit 1 from the data, as it is the cause for such a great transit depth. You might ask yourselves, why does visit 1 have such a great transit depth? And that's because there were problems with our observations. So during visit 1, the guiding system failed. So the guide camera completely lost track of the guide star, leading to orbit 3 not having any data at all. And then it locked onto the guide star, but not very successfully. So orbit 4 data were shifted to the edge of the detector and cut off. And then in visits 2 and 3, the scanning mode of HST failed, which led to orbit 3 not capturing any useful data. So we decided to proceed with only visits 2 and 3, and here I show the normalized place-folded white light curves. And as you can see, the transit depth is a lot shallower, and that is because a lot of the mid-transit data are missing, but we calculated the transit depth to be 0.00078, which is a lot closer to the predicted value. However, the data proved insufficient to extract the transmission spectrum with Pac-Man, which is why we decided to continue with GJ1214b, which is a very famous sub-Neptune of temperature 600 Kelvin, radius 2.74 Earth radii, and mass 8.17 Earth masses. And we use archival Hubble Space Telescope Widefield Camera 3 data from 2 visits taken in 2013 in March. And we decided to continue with GJ1214b for 2 reasons. And the first reason was to show the remaining steps of the pipeline with a sub-Neptune with relatively similar parameters to TOFF61c, which we do here. So again, in stage 21, the spectrum is binned into wavelength bins. In stage 30, the spectroscopic and white light curves are fitted, detrended, and the systematics are removed. Here I show the white light curve. And then the transmission spectrum of the target is extracted, which I show here in more detail. So this is the detrending process. And on the right, I show the transmission spectrum of GJ1214b, which appears to be flat within uncertainties, which matches previous observations of the target. And then the second reason why we decided to proceed with GJ1214b was that so we could simulate a transmission spectrum for our target. And we did this by adjusting the error bars to our target's parameters and took into account the relative transit durations and J-band magnitudes. We plotted TO561c transmission spectrum for 4 visits, as that was originally what we had been scheduled to observe. And we show the results here. As you can see, it appears to be quite flat, but that is just because we used the GJ1214b data. And the error bars appear to be really big, but if you take a look at the vertical scales, you'll see that they're actually about 3 times smaller than the GJ1214. And then that prompted us to be able to test different atmospheric models to the data of TOFF61c. And it is clear that we can reject the clear atmosphere with almost total confidence, as it had a chi-score of 114, which corresponds to a more higher than 10 sigma detection. And then in the future, visit 4 has been scheduled for February 2025. If that's successful, it will make us be able to further constrain the atmospheric models. And here I show a simulation of what could happen. And the error bars are bigger because it's only 1 transit. And also, we decided to simulate the data with the James Webb Telescope in the range from 3 to 5 microns. And we can clearly see that there are some spectral features of the most dominant molecules for this target, which include methane and also carbon monoxide. There is a small peak around carbon dioxide, but it is actually not predicted because the peak should have been a lot bigger. And then the gray lines are just partially saturated data. And these are my conclusions, and I'm happy to take questions. Of this.
Thank you. This is very interesting. Talk. I was wondering what causes the difference between different models of energy speed. Is
Mhm.
we have weak clouds and little clouds, but in this example, big clouds.
So weak clouds and medium clouds were simulated using ExoMast, and that uses the no, ExoMast, ExoCityK, and that uses the Fortnite grid. So it uses a different strength of cloud coverage. I can't remember off the top of my head, but I think it's 1 times and then 10 times that of molecular hydrogen at 350 nanometers. And depending on the strength of the cloud, it allows more or less photons to penetrate the atmosphere, and so causes larger or smaller spectral features.
Yes, I was going to ask that you go from low temperature, it's clear, then you go through these various different stages, and then back to high temperature, it's clear again.
Mhm.
Why is that? Is that different physics?
It's still theoretical. We're not exactly sure why it happens, but I think just hazes and clouds have been observed to form around those temperatures, but it's still very unclear what the actual limits are.
Surprised, but obviously it's not in the field of these very high temperatures. How do you maintain the atmosphere at 900 K? What are the host stars? It's just people even just boil it off.
I'm not entirely sure about the theory behind how planets can keep their atmospheres, but
So let's thank again.
I've got it. Possibly.
So we're now switching back to high redshift with Yazmin Bath, who's been working with Dan Schwartz here on trying to include on channel the explicit evolution using general relativity. Dan is a man of not many words, and he'd like you to know that how impressed he is with Yazmin's project. Those of us on Dan's corridor will miss the long extended meetings where Yazmin and the Chancellor are talking about but hang on many different topics.
I guess that's just me then, isn't it?
So Yazmin will be telling us all about using gravitational lensing to resolve milliarcsecond X-ray structures at high redshift AGN.
Sorry, 1 second.
Share that.
Yeah,
Oh,
I'm
sorry.
trying to. How do you get to the Zoom? Okay, there we go.
All right. Oh, need to remove the floaty thing. Oh, yeah. Wonderful. Okay. So, hi, I'm Yazmin Bath, as I've just been introduced. I've been working with Dan this year on my master's project in collaboration with the University of Southampton, and I have several collaborators as part of the gravitational lensing for astrometric determination team. And I've been using gravitational lensing to resolve the milliarcsecond X-ray structure of high redshift AGN this year. So we should 1 second, sorry. We should probably start with what gravitational lensing is. I'm sure you all know the basics, where the light from a quasar will be bent around the foreground galaxy between us and that source. This ends up focusing rays into apparent images on the sky. This can form between 2 or 4 images, depending on where the source lies in relation to the lensing galaxy. But because these rays from the source are focused into these images, we can see we get a lot more information about the source. So we can increase Chandra's 0.5 arcsecond resolution which at high redshifts of 2 or 3 corresponds to about 4 kiloparsecs. We can resolve now to sub-kiloparsecs, even parsec scales. This allows us to potentially resolve things like X-ray jets. Here's M87, which is in the local universe. Obviously, we can't do anything that looks quite this pretty, but we can determine offsets from known core emission. This allows us to study collimation and formation of these jets and how they interact with galaxies, drive winds, and drive galaxy feedback mechanisms. We can also search for dual and binary AGN systems at parsec scales, which is very important as we don't know how our galaxies evolve to be what we see today. So we start with where I chose my source and why I chose my source. This is a quadruply lensed quasar with 4 distinct images. It's previously been studied to do things like analyze a Hall's constant. It has a lot of spectral analysis across many bands, but I chose MGO414 because it's got 20 Chandra observations, 11 Chandra observations over 20 years. Sorry, that's a typo. It's at a source redshift of 2.64, which corresponds to that 8 kiloparsecs at 1 arc-second range, which is very hard to spatially resolve. We want to see what's going on. It has this unique configuration where there are 2 images that are much closer together than the other 2. And this means we can compare it much easier to other bands that have the same configuration because we know where the images are. The fact that the images A and B are so close together means there are more rays focused into this area. They have a higher magnification, and this gives us a lot more counts to work with. We also have many detailed complementary data sets in optical, in IR, in radio, and a very important data set that we've taken from is the VRBI data by Ross et al. 2000. And this gave us an indication that there were large extended radio jets in the system, which is likely a known cause for X-ray jets to occur. So how do we take this observation at these scales of separation of 2 arc-seconds and make it milliarc-second scale at parsec resolutions? So we have to start by simulating the X-ray source. These are all all simulated separately as 4 different images as point-like sources, as we can fairly comfortably assume for the most part, most X-ray sources are point-like sources coming from the center of an AGN. But we want to do this because we don't have that many counts in the original images, so we don't have very many statistics to work with. So we first simulate these, and we want to fit them to trial image locations. In order to do this, we have to parameterize the lensing galaxy. So here we have 2 lensing components and 2 caustics, where inside here we form 4 images, and outside here we form 2 images, and outside here we just see a normal source. So in parameterizing this lens, we used the offsets given by the VRBI of the core, or what was assumed to be the core radio emission, and we use these offsets and parameterize the lens to give us the VRBI source, which is here. And we can then assume that maybe or it's likely that the X-ray is going to be coincident with this core position. So we take a grid filled in this area in order to guess and where the X-ray source may be. So we can fit those simulated images to these image locations at every source, because every source will give different image locations. And then we can compare them using a maximum likelihood statistic. So this looks like a very ugly equation I'm sure a lot of you have seen before, but we basically are saying that we take the simulated images at the trial image locations, and we want to see how well they fit the real observations. And when they fit best, this statistic C will be minimized. So in each one of our observations, 11 observations, we'll use the same grid, and we will have a maximum likelihood for each position, and the minimum in each observation is where we would determine the X-ray position to be. Furthermore, we see that across this grid, each maximum likelihood compared to the final maximum likelihood at the X-ray position will be distributed like chi-squared with 2 degrees of freedom due to evasion prior in this equation. So now we can move on to the results that I found with this technique. And I will explain what's going on here because it looks like a lot of information to divulge in right now. So we have the caustic again, where in here we form 4 images, out here we form 2, so we can reject all positions that lie outside the caustic. We have the final X-ray position as a black cross. We have the VLBI core position as the red star. And then we have our contours, where the yellow corresponds to 1 sigma, and as we move outwards, 90%, 95%, and 99% chi-squared distributions. So we can see for the majority of our sources, we can exclude this VLBI core position to more than 99%, which is very interesting considering we would like to think they would possibly overlap. And the only one that doesn't is this one here, which is excluded to 95%. And the contour size are dependent on the counts in the real observed image, where the contours are larger for less counts, as the maximum likelihood will be lower, so the difference with chi-squared will be larger. So we see these observations have the longest exposure time, and these observations have a lower exposure time. So if we take all of these observations, maximum likelihoods at every position in the grid, we can then sum them to form a final position across all the observations across all of time. So here we see we have the same convention where the black X is the final X-ray position, the red star is the VLBI core position, and now we have blue triangles which correspond to the radio jets that were found by this paper. So we see here that there are 2 jets, it's a dual jet system. However, this image is formed because of the perturbation from the secondary satellite that lenses our source. So we expect in the source plane, when you would be resolved back behind the lensing galaxy, that this would be a straight line in one direction. However, we see that it keeps this configuration with a perturbation. This leads us to believe our mass model that we use to parameterize the lensing galaxy may be unfocused, it may not be quite right. We aren't sure yet. However, the most important result from this is the fact that these contours are now very, very small, purely due to the fact we have so many counts in so many observations over a lot of time with high spatial resolution from Chandra. So this offsets about 6 milliarcseconds, plus or minus 1 milliarcsecond, which is incredible considering Chandra has a 0.5 arcsecond resolution. And this is about a 50 parsec gap, and the area enclosed in this contour at 1 sigma is 0.03 milliarcseconds squared, which is incredibly high precision. And we aren't really sure what explanations there are considering this configuration yet. So we need to look at the spectral results of our source to be able to determine what we're looking at in X-rays. So here we've fit just a power law with intrinsic absorption, galactic absorption, and a Gaussian line to model an ion line. We found that there is about intrinsic absorption at the source of about 3 times 10 to the 22 centimeters per centimeter square, which is very heavy. We've known from previous papers that this is already known to be a heavily reddened source. And this probably comes from the torus. We also see an ion line at 6.22 kiloelectron volts in the rest frame, which is indicative of a reprocessed K alpha line, which is just reflection of X-rays of the accretion disk. And this model obviously fits very well, considering our range is about plus or minus 2 sigma. This leads us to believe that we're actually looking at the core X-ray, the X-rays from the core, which is very interesting considering we have an offset from what was thought to be the radio core. So overall, we have this unique high precision technique that we can use on Chandra observations to increase our resolution from 0.5 arcseconds to milliarcsecond scales. And we've determined that we see core AGN emission, and we have further work, which includes testing some new mass models. Thank you, and I welcome any questions.
So if I remember correctly, you have 2 jets parallel to each other?
It's a dual jet system, so we should see something along one of these lines from this core position. So I have, this is what we see in radio in all of the 4 images. So this is probably the best example of where we see a core and 2 jets.
Actually, the question I had was going to ask it. possibly answering by this question.
Yes.
Now that I look at it, I was gonna ask, going to the very beginning, how are you sure that A and B are not one image of the quasar?
So
Get like,
yeah.
we're so close together.
So you can actually resolve two peaks in our observations, where in you're talking about this image, right?
Yes.
There is actually like a peak here and a peak here, which are very obvious because they are very close together. And I think they're at about a 0.4 arcsecond separation, which is below what Chandra can really resolve. But yeah, we can be sure that that occurs because in all the other bands we see 4 images. So obviously in the radio we see 4 distinct images of the source, and it's an achromatic effect. So if there's 4 images in one band, there should be 4 images in every other band.
Okay. That's why we like continue.
So there. No, that's thank you. Yes.
That looks like something. You got it?
So we're going to be switching back to more local matters here. Well, we now hear from Maja Lilley, who's been working with Federico Frascati.
Right.
Unfortunately, Federico is not able to be here today, but he's here with us in spirit and hopefully soon. Federico is constantly giddy about the potential applications to both exoplanets. Oh, they're right. Well, that ruins my source.
I have learned in presentation mode already.
Well, no. I think it's fair to
No,
say that
wait,
you're
what's
possibly
the-
thinking about
oh yeah, I need to
the
do this in the next
applications
one.
work.
Mhm.
So I need to put this in presentation mode and then set it up right.
Um,
Learning.
No, it's totally fine. It's always confusing.
This talk involves a lot of code and numerical development,
Perfect.
almost as much
I'm an
effort
expert.
as it
This
requires
one,
to
yeah.
do
And then
something.
you go. Sorry.
And I really
Okay.
want
Oh,
to
yeah,
spare
no,
you the
that's
details
something.
of all the
Actually,
coding
it might
details.
be
Yeah.
doing it already.
I think
No,
we'll get
it's-
back now.
If you do want to know more, please ask. She will love you for it. So
Okay,
maybe we'll
good
be
job.
talking about modeling high energy stellar energetic particles using the focus transport equation. Go.
Hi, yes, as Doug said, I'm Mia, and I've been spending the last year working on my project with on the supervision of Federico Fraschetti. And in our project, we looked at modeling energetic particles using the focus transport equation. It does not go. Oh, hold on a second, sorry. There we go. So I'm going to start by talking about why we're interested in this. So energetic particles can influence the evolution of an exoplanet's atmosphere through ionization mostly, and this can affect how habitable a planet is. And this is something we're very interested in, as we're constantly looking for planets, other planets in the universe capable of supporting human life, and even possibly those that already have life. But unlike the solar system, there are many systems that are quite compressed. So this image here, the top image is shown entirely in this disk here compared to the solar system. And as you can see, that's entire system fit before Mercury. So this system is going to experience a very different distribution of particles to the solar system. However, we're also interested in systems similar to the solar system, but younger, as this would allow us to maybe estimate the kind of particles that were bombarding the Earth when life developed on this planet, which would be very interesting. So along with energy particles, I'm sure everyone here knows what coronal mass ejection is, ejection of plasma from the stellar surface. And when colliding with the next planet, it could be capable of completely stripping away its atmosphere, which would render it completely unable to host life. However, coronal mass ejections tend to be limited by very strong magnetic fields. And this means, although they have devastating consequences, they tend to be quite infrequent and so are unlikely to dominate atmospheric evolution. Another factor that we could consider would be galactic cosmic rays, which are energetic particles that come from outside of the system. However, as they're not coming from the host star, they have to fight against a very strong outflowing stellar wind to get to the most inner reaches of a system. And as shown by the image with the TREPPIST system, that's a very close in system, which means galactic cosmic rays are really going to struggle to get to those reaches. And as such, galactic cosmic rays are also unlikely to dominate atmospheric evolution at close-in exoplanets. Stellar energetic particles are energetic particles that come from the host star, typically during stellar flare events. They propagate outwards in the stellar wind, can be influenced by the magnetic field, and then reach exoplanet orbits where they can bombard the atmosphere and then potentially ionize it. And due to the consistency, they are most likely to dominate its evolution, and therefore they're what we focused on in this project. And this figure here is from the GO spacecraft, which monitors proton flux at Earth. And this is just over this past week when we could see the aurora even as south as Boston. So as you can see, it starts out quite low and then goes to almost 1,000 times that base level in the red line. So you can really see the effects of the stellar energy particles. Again, in close-in systems, like the TRAPPIST system shown, because of how close they are and the nature of young active stars to have faster rotation periods and stellar wind speeds, those close-in exoplanets are more likely to experience a high flux of high-energy particles compared to further out planets. And that's very interesting. But high-energy particles tend to have longer focusing lengths, sometimes on the order of the system size. And what that means is that they can travel a very long way without really being influenced by the magnetic field or being focused by it. And as you can see from this figure, which in yellow and red displays two different Parker spiromagnetic fields, if a particle was to just stream out in a radial direction, it would be very different to the magnetic field. It would not be aligned with this magnetic field. And we call this pitch angle anisotropy, which again is shown in this figure here. So the blue arrow shows the direction of the magnetic field, the red shows the particle velocity, and mu is the cosine pitch angle, which is the angle between these lines. So high energy particles will have a higher level of pitch angle anisotropy, whereas low energy particles, not so much. And previously, the Parker equation has been used to model these distributions, and it works very well on low energy particles. However, it does not account for high pitch angle anisotropy, which, as we just discussed, is prevalent in high energy particles, which means the Parker equation can sometimes break down or not give reliable results when looking at high energy particles. A much more suitable equation is the focus transport equation, as it does account for high pitch angle anisotropy. And there are many different versions of the focus transport equation. The version that we used is shown here. And it's made up of three main terms. So the streaming term accounts for motion of particles along the magnetic field line. The focusing term accounts for the effects of a converging or diverging magnetic field, which will focus or defocus the particles as they travel. And the scattering term is the pitch angle scattering, which will change particle directions based on due to fluctuations in the magnetic field. So we wrote a numerical code to solve this equation, and here are our results. So this plot on the left shows the particle distribution function at 0.1 AU with time, and this figure on the right shows the effect of stellar wind. So the two speeds that we considered were 1,000 and 2,000 kilometers per second, and the particle energy used for this figure was 100 megaelectron volts. Looking at this figure, if you take a time slice and then plot the particle distribution function against the energy, you get the spectrum, which is shown here. And this is in log-log space, very linear. So as you can see, these particles are all very closely following power laws. And this is very reassuring. So we injected a particle power law with an exponent of -3, and the power laws have been preserved. They can be lost sometimes in the transport. But as I said, it's very reassuring as we were the first people to use the focus transport equation, this high energy regime. So to see this distribution, which is what we would expect, really shows promise for future work. We did consider different rotation periods. 3 different rotation periods are shown on this figure down at the left, but you might struggle to see them as they overlap almost perfectly. And we think that this is due to the close-in distance that we looked at. So as you can see from these two spirals showing 4 and 27-day the rotation periods, the magnetic fields of such stars, they obviously look very different. However, if you just look at this first band, within this first band, they actually look quite similar, and they almost even look radial. So we think that if we look at distances further out, we should start to see the effects of the differing rotation period. And that's something we are currently working on. It would also be interesting to look more into different stellar wind speeds, as we only considered 2 speeds and we only considered them for 1 particle energy. So although there was a difference there, no real conclusions can be drawn until we look into it further. And ultimately, the goal would be to compare stellar energetic particle fluxes to the GCR fluxes at the same distance, and do this at multiple distances until we see the point where GCR flux becomes relevant, if not even dominant, to the evolution of exoplanet atmospheres. Thank you for listening. Are there any questions?
Yeah, nice talk. Thank you. Maybe I missed this, but what are the wind solutions that you use for this? You said you use just two wind solutions?
Yeah, so we considered the speeds 1,000 and 2,000 kilometer per second, and these appear. So we have a lot of variables hidden in this equation. But yeah, so we consider. Yes, it's the same. So we, instead of consider it as a particle, like individual particles in a wind, we essentially consider it as a distribution, and the wind speed.
So the speed of that. The waves are bigger than the wave, but we just need the spot out of the path.
Do you have any other questions? So I mean your discussion on the pathway, the phase angle shift, and that's more noticeable in the high energies, which hasn't been studied before. But that's presumably also going to be similar to your plot there with the rotation speed. You're going to see it more further out than this inner region.
Possibly. I mean, we still did see it. So this is also at 0.1 AU, and there is obvious difference between these two lines. So yeah, it would be potentially different furthering out, and that's why I think with galactic cosmic rays, because the wind is, as it's spreading, it's getting weaker, so there should be a high flux of GCRs out as there's less to fight against. So yeah.
That's the time.
Thank you.
So as a note for those of you thinking about writing proposals, you don't need to come up with a project like me as well. You just have some throwing, CMEs left, right, and centre, but it doesn't help. It doesn't hurt to so our final speaker today is Alex Ostridge, who's been working with Raphael Galazza along with Dan Schwartz. Raphael is also, he's now the only person, the only supervisor who's not been able to be here today. But he wanted me to say that it's been a pleasure working with Alex this academic year, so it's just going to go on for a while. He's an extremely kind person and a very capable and independent researcher who came to the CfA wanting to learn about gravitational learning and machine learning, gravitational lensing, sorry, and machine learning, and is leaving equipped with the skills to become an expert on both fields. And that's because of his own effort, dedication, and desire to learn. I thank him for great discussions about the meaning of activation functions and biases, and for always taking initiatives to try new things. I've also enjoyed discovering that he's into jazz music and is a seasoned traveller. Alex has great potential in his career, regardless of what he chooses to do, and I wish him the best. Luckily, he and I will be continuing to work to complete the research paper. So with this, let's welcome Alex to talk us about using machine learning to characterise gravitational lensing.
Thank you very much. So yeah, as I said, I'm Alex Ostridge, and I've been very lucky this year to work with both Raphael and Dan on characterizing gravitational lenses using machine learning. So as Yazmin mentioned earlier, and as a lot of you know, gravitational lensing occurs when light passes nearby very massive objects, and that light is bent and forms images due to the time it takes to arrive to the observer. Now, the position of these images and the flux of the images themselves are highly dependent on the distribution of the lens, the mass distribution, as well as the masses between us and the lens. So any other galaxies or components between us. This can be incredibly interesting as we can delve into the properties of the lens, as well as dark matter between us and the source. And it's an incredibly interesting field currently, as we're expecting at least 200,000 gravitationally lensed sources over the next few years with the Roman, Rubin, and SKA sky surveys. Now, the area I want to focus on is to using gravitational lensing to improve our X-ray resolution, because for X-ray sources with Chandra, we only have 0.5 arcsecond resolution, and this is not a high enough resolution to accurately resolve jets or binary systems or other radio counterparts to X-ray sources. So instead, we can look at simulating these lenses and the sources that Yaz did earlier, and we can simulate moving these sources, which causes large changes in the image positions. And by comparing simulated image positions to the real observed ones, we can refine in and hone in on a more accurate source position, much better than the 0.5 arcsecond resolution that we can get with Chandra. Now, to do this, we require a detailed mass model of the lenses. So this parameterizes the mass distribution of each lens, and generally includes the position of the lens itself, some sort of scaling parameter for the mass, the ellipticity of the lens or lensing components, and any external shear from clusters or nearby galaxies. One of the most common ones that we use is single isothermal ellipsoids, which take a mass parameter and the surface mass density scales with elliptical radius. Manually making each mass model can take between days or weeks for simple cases, and if you have particularly complex cases, each mass model can take even months. And given the 200,000 expected cases in the next few years, this is a long period of time, and we wouldn't be able to individually create a model for each lens. So my aim for this project is to speed up the time it takes to parameterize these lenses and hopefully get to the point where it only takes a few minutes per lens to refine and create these models. So the way I'm using to do this is through machine learning, which is a set of techniques and algorithms that allows computers to learn relationships in data that without a human explicitly inputting or programming it. So the method I use in particular is using neural networks, which take a set of inputs on the left, and the numerical inputs, they propagate them through a network where a combination of linear and nonlinear operations are applied into a numerical output. And given ground truths for both inputs and outputs, we can compare the outputs to the real truth values, and then edit how we do these operations in the network. So each node here, where we have a input of a number, gets connected to another node where a linear operation will take place by a weight, which is just a numerical multiplication of the value. And these weights can be varied, which iteratively gets varied as the network compares the predicted outputs to true outputs and tries to refine the predictions to higher accuracy. So it propagates trial or testing data and then receives a bunch of outputs. We then compare them to the true values and then change the network to more accurately predict them. The current problem is we only have about 50 to 100 lens sources in X-rays that have mass models been created for them to a high accuracy. This isn't enough to accurately also use machine learning to learn relationships between this. We require many more examples of data. So I've simulated my data. For this, I use a simple isothermal elliptical model with this parameter range for the mass parameters and the ellipticities. We don't include galactic shear for these, but on the right here, you can see a region of all the sources plotted for one mass model. In this case, these edges of the plots are the caustics of the lens. So this is where a source at this position would theoretically have infinite magnification. A source that's outside of this area would only have 2 images. So we've only chosen sources within the inner caustic to have 4 images, such that we have a higher count in X-rays, as well as having multiple 4 images allows us to create a reference frame on the sky, compare it to radio positions or optical. Each set of lens models has 10,000 sources per model, and they were all concentrated, well, a lot of them were concentrated around the edges of each caustic, as that's where sources produce the highest magnification, or the images have the highest magnification. So when inputting this into the neural network, we require features that can fully describe the lens while being invariant to rotations. On the sky, we don't know what rotation the galaxy will be in. So I've chosen a set of features that include the distance ratios between 4 of the images. So around here, here you got the lens center, the source in blue, and the 4 images in orange crosses. The caustics of this lens are also plotted in blue. So we have the distance ratios between the images, the area enclosed by each of the images, the scaling distance where we sum multiple lengths of these distances, the flux ratios of each image, as well as the positions directly of each image in comparison to a chosen point, which in this case was the intersection point of each image. So I tried a wide combination of these 5 parameters and over a wide set of architectures of neural networks, including multiple different amounts of nodes or combination of operations for predicting both ellipticity and mass parameter. Now, I found that only using distance ratios and image positions work best for ellipticity, and I added flux ratios seem to give better predictions when using mass parameters. By making small variations to these predicted parameters, we can then refine the model to more accurately predict image positions. So these networks will give an estimation for the parameters of a lens, but they won't give the final true or most accurate parameters. So instead, we can then slightly edit these, simulate a set of image positions, and compare them to real observed data. And by continuously making very small variations to these predictions, and then re-simulating images and comparing again to real data, we can refine these models, hopefully within a short period of time. So these are the results from my mass parameter predictions. On the bottom here, you have all the mass parameters for between 0.1 and 5.5 arcseconds. And on the y-axis is the predictions. These are plotted for all ellipticities, for all mass models. And you can see the distribution of each prediction plotted as a violin plots. Each of the red lines is the 2.5% and 97.5% percentiles, so within which contains 95% of our data. On the black dotted line is an identity line, which is the true values of what we want to be predicting. And as you can see, the majority of the data is predicted very accurately for most cases. There's a few, when you go to higher mass parameters, it tends to underpredict them, and for lower mass parameters, we tend to overpredict. I have plotted the same for the ellipticities as well, where the majority of cases in the 0.2 to 0.3 bands predict very accurately, and we tend to over and underpredict at the extreme ends of 0.6 and up in ellipticity and closer to 0. But the main thing with these is they were accurate enough for us to be able to create mass models that could predict a milliarc-second resolution. So we tested this by creating, simulating 100 lenses, each single isothermal elliptical lenses with random parameters and random rotations. And then I tested my predictions on them, predicted the mass and ellipticity parameters, and then I tried to optimize a mass model for these parameters by comparing the observed image and simulated image positions. I was managed to do it for 70 of 100 of these cases, and all the image positions were reproduced to an accuracy of 0.5 milliarcseconds, which is a significant step in comparison to the previous 0.5 milliarcseconds. Each of these were achieved within 2 minutes per model. I then tested this again for 3 galaxies which we have observed in X-rays, and each model could reproduce their own image positions within 0.5 second, with a 0.5 milliarcsecond accuracy within 2 minutes for each model, which is a massive leap from the weeks to months that it can take to make these models. I'm hoping that this can be used on the incoming 200,000 sources to then see which of these lens systems are actually interesting to look at in X-rays. In the future, I would like to incorporate external shear into this and into the predictions and the training data. But that's stuff for the future. But yeah, thank you very much for listening. And if you've got any questions.
Do you have any questions, Sean?
So most of the lens data of galaxies comes from ALMA, and the ALMA maps are way more complicated than the X-ray maps. Do you think this would be applicable to direction of lenses for ALMA data?
As long as we have 4-inch positions from the ALMA data, I don't know exactly what other data is returned, but I only need 4-inch positions and the fluxes for the reduction or like making of these mass models. So as long as we have that data, it should work. It will work best on the simpler lenses, but hopefully we can improve that for more complex lenses as well.
Yes. Well, one of the things about ALMA, of course, is that people do the lens reduction in the UV space rather than the image space. Something that, yes, this is a solution to a possible future problem.
This should also apply to all bands of light, as the mass models are achromatic as well. Thank you.
So do you have a feeling for what external shear does to these models?
External shear will just act like another elliptical galaxy lensing, or can be assumed to be. So it will just add another perturbation to the image positions. We do allow the shear to slightly vary during the refinement of the model, but we haven't predicted for it. There is a small degeneracy, or a large degeneracy actually, between shear and ellipticity. So quite often the galaxy will seem as though it's got very high ellipticity, but it's not. It's a lot of it is contribution from shear. So it's just more perturbation that we should be able to predict.
Well, so guys, thank you for all of it.
Thank you very much.
Thank you for listening and sending your proposals.